Okay, where we need to pick up then, after that last example, is with the idea of polar coordinates. We usually define the position of a vector in a two-dimensional space, a plane, if you will, according to directions like x and y with unit vectors I and j. But that becomes complicated when rotation is involved. Then in that case, we tend to use polar coordinates. Or the polar coordinate system. And in that, we give the location of a point that you could call P. And that the location of that point is still given by two coordinates. Only we call those polar coordinates. One of them is known as the radial coordinate. And that is called R for radial. Funny how that worked out. And that is the distance of P from the origin. And the other thing we would want to know is the angle. The angle is called phi, or phi if you prefer. It's the Greek equivalent of pH in English. The book tends to draw it something like that. I usually draw it more like a circle with a line through it, but it's the same letter either way. And it's the angle made by the vector with some specified direction. And that basically specified or direction is usually the x-axis, the positive x-axis, which means these coordinates are sounding a lot like the coordinates that we traditionally have used. And they are up to a point. One difference here is that the angles are not measured in degrees, but in radians. And to convert a number of degrees to radians, mathematically, what you do is you take the number of degrees, whatever that is, we'll call it x, divided by 180 degrees times pi. And it's also important to keep in mind that if you're going to be doing calculations involving radians on your calculator, you have to change the setting. If you have a calculator like mine, and I think this model, although maybe not this color, but this model is the most common one out there for scientific calculators. If you look down in the lower right-hand corner, you'll notice it says DEG. That stands for degrees. So any trigonometric functions like sine or cosine or tangent or anything that you put in here is going to be using angles marked off in degrees. If you're going to use radians, what you have to do is look for this button here, the one that says DRG. If you press that, you notice you get a choice between degrees, radians, or gradient. And what you want to do is use the right arrow key to underline radians and then hit enter or equals down at the bottom, and you'll notice that that little sign changes to RAD for radians. So that's what you need to do if you're going to be putting numbers in terms of radians. And then basically you can just enter, basically radians are given as some number times pi. And for pi, you can just use the pi key on the calculator, or you could put in 3.14. But as long as you've got a key right there for pi, you might as well use that because the calculator knows pi to a lot more places than you do. I mean, unless you're one of these science geeks who enjoys remembering pi to thousands of places. 3.14 is about as far as most people would go in writing down a number for pi. So it's better to use this than rounding it off. Remember though, if you go back to even if you turn the calculator off and turn it back on, it's still going to be in radians mode. So if you want to go back to using angles in degrees, you have to push that button again and use the left arrow this time to go back to degrees and then press enter. And you'll notice you'll be back in degrees. Okay, back to where we were. A radial vector begins at the origin and points to P. Radial direction is described by the unit radial vector which is R with a hat over it. And there's a unit vector T, which describes a direction perpendicular to that. Okay, so instead of I and J as the unit vectors for X and Y, we now have R and T as the unit vectors, is essentially what we're saying. The positive T direction just tells how phi changes in the counterclockwise direction. But that's kind of like just like saying that you measure phi going counterclockwise from the positive T direction, just like we do with the positive X axis in our normal two coordinate system. So in our normal XY system, known as Cartesian system, point P would have coordinates X and Y. And in polar coordinates, its coordinates would be R and phi. Okay, so you can find the X and Y coordinates of a vector in polar coordinate system. simply by this. Or sorry. Okay, so if you have a vector that's called r, the x-coordinate would be r, that is the magnitude of the vector r, times cosine phi. And the y-coordinate would be the magnitude of the vector r times the sine of phi. But remember, phi has to be in radians. If you put it in degrees, everything's going to go wrong. So what we've got here is kind of a coordinate system like this. We've got a vector that points to point P, and we can call this the x direction. The angle phi could be defined as that. And furthermore, the vector itself defines the r direction, and perpendicular to that would be the t direction. Okay. Maybe the best way to illustrate that would be to try an example. Somebody is out metal detecting in this example. And you're starting out at in searching for treasure at this dry well. So the dry well is going to act as the origin, and you find a silver coin at a spot 20 meters from the dry well. In a direction 20 degrees north of east. Then you find a gold coin at a spot 10 meters away. And it's in a direction 20 degrees north of west. Oops. So what you want to do here is find the polar and rectangular coordinates of the coins versus the well. Okay, so for a solution here, we start with defining what the origin is. It would make sense to make the well the origin, because that's what everything has been, that's what everybody's been talking about versus the well. So you might as well use that as the starting point. And from that, we can draw this kind of diagram here. Okay, so we have the four directions. The first coin is found at a distance that's 20 degrees north of east. Well, 20 degrees north of east just means 20 degrees, because east is the direction from which we normally measure angles in this system. So 20 degrees. Okay, the other angle is 20 degrees north of west, which means you can look at it as basically being 20 degrees short of a full 180. So that angle is 160 degrees. Or, yeah, 160 degrees. So we'll say 20 degrees north of west. So there are your angles. Anyway, the magnitude of the vector that points to the silver coin is 20 meters. The magnitude of the vector that points toward the gold coin is 10 meters. 20 degrees in terms of radians is going to be equal to 20 degrees over 180 degrees times pi, which is the book likes to use fractions for these. So you can think of that as pi over 9 or 0.111 pi, because 1/9 is 0.111. 160 degrees would be 160 over 180 times pi, which is 8 pi over 9 if you want to reduce the fraction, or 0.889 pi, whichever you prefer. Okay, so pi over 9 or 0.111 pi, that would be phi sub s for the angle of displacement of the silver coin from the well. And 8 pi over 9 or 0.889 pi would be phi for the gold coin and the angle of displacement for the gold coin. So the polar coordinates of the silver coin would just be rs Phs, and that's going to be 20 meters and pi over 9. Or 20 meters and 0.111 pi. So for the gold coin, that's going to be RG Fiji, Fiji, and that's going to be 10 meters and 8 pi over 9, or 10 meters and 0.889 pi, if you prefer to do it that way. All right. For the silver coin, the rectangular coordinates, all right. For the silver coin, will be xs for x coordinate of the silver coin. Will just be r times cosine. So that's the r, that is the magnitude of the displacement for the silver coin, times cosine of the angle of displacement for the silver coin. And that's going to be 20 meters times the cosine of pi over 9, or 0.111 pi if you prefer, which is 18.79 meters. And for the silver coin, it's r silver times sine of phi silver. And so that's 20 meters times sine of pi over 9. and that is 6.84 meters. Or in other words, 18.79, 6.84 would be the coordinates for the silver coin. Okay, so the rectangular coordinates for the gold coin. Done the same way. The x-coordinate for the gold coin would be the magnitude of the vector of displacement for the gold coin times cosine of the angle of displacement for the gold coin. That's 10 meters times cosine of 8 pi over 9. And that comes out to be, let's see, that comes out to be negative 9.4 meters. And the y-coordinate of the gold coin, again, is going to be rg times sine of phi g. And that's 10 meters times the sine of 8 pi over 9. And that comes out to be 3.42 meters. Or in other words, negative 9.40 meters and 3.42 meters. Whoops, would be the coordinates, the rectangular coordinates. Okay. Well, that was fun. The next topic that we need to get to is vectors in 3 dimensions. And we're a little short of the time for this video, but as long as it's a new topic, I think I'm going to stop segment 2 here and go on with the third part in a moment. So I'll see you in the third part.